Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at Uni of Adelaide. It's semester 2, 2023, and this is a revision seminar for real analysis. We've had a bit of a discussion about what's in the course and what people want to talk about. And the big ticket item at the top of the list is, how do you decide how to go about doing a proof? But the particular things that I've been given are, well, there's like 3 main flavors of kinds of proof. There's induction too, but that doesn't come into real analysis very often. Induction is designed specially for natural numbers. But to be fair, you do have sequences, so you can theoretically do things with induction on sequences. So I'll just stick it in brackets, induction. But technically, induction can use any of these along the way as part of its proof. Okay, so I put them in this order for a reason. Most people prefer to try this, to do direct if they can, and then if not, do contrapositive, and if not, do contradiction. So that's my first piece of advice, is that most people prefer to read a direct proof rather than either of these ones. And so if you can think of a direct proof and give it a go that way, then that's a good choice to try first. Okay. So that's advice number 1. Most people prefer a direct proof, so probably good to try that first. My second piece of advice, and it's not as useful for an exam as it is for assignments, is it's okay to try one and abandon it and then try something else. My advice for trying and abandoning in an exam is to not cross out either of them until you've finished one of them. So most maths markers will read something that's crossed out anyway, as long as you don't, completely cover the whole thing in ink, right? So just a single line will be fine. Yeah, well, yeah, and if it makes a difference between one grade band and the next, then they'll go looking, usually. But in general, the point of an exam is for you to show what you know and show what you're capable of. And so if that's a place where you've shown that you know something, then that's where they'll go looking for it. So it is never bad to have more things on there for them to look at. So just want to point that out, but it is okay to try one and abandon it. My general advice is to sort of do a thought experiment version of it and go think for a minute and then try. But then even if you've committed to starting writing, it's okay to abandon that and try something else. And it's all right to write notes on there in an exam to say, I tried this one, didn't work, so please read this other one or whatever. Or if you've crossed it out and you decide to go back to it, cross out the other one and say, please read this first one, like give notes to the person reading it. If you're lucky, Finna will have designed the exam in such a way that it should be a little more obvious for most of them than it is in some of the assignments. But who knows? Something can seem obvious to the person who wrote the question and not obvious at all to the person trying to do it, as you've experienced during the course. There have been times, famously, that one with the sequence with the A on 3 plus 2 on A or whatever it was, there was a sequence, and when we all looked at Finna's solution later, it's like, where the hell did you pull this from? So Okay, good to, can I add that to the feelings? So that, where the hell did that delta come from is the feeling that we're thinking about. Right. Okay. All right, cool. So the second thing is, yeah. Don't scribble it out. Okay. I forgot my train of thought now, but they're all good thoughts. Okay, the third thing is, and this is hard to say, but I'll make an attempt. Statements that have negatives in them are easier to prove by contradiction or by contrapositive. So if your statement is saying that something isn't something or doesn't have a property, it's easier to prove it by contradiction. It's much easier to talk about things being or having than it is to talk about them not being or not having. Yeah. So, and if you're, or not existing, it's much easier to talk about something that exists than to talk about something that doesn't. So if the thing you're trying to prove is not a kind of thing, this is really hard to say. So like not continuous, for example, not a kind of thing, not existing, not having a property, then it's much easier to do contradiction or contrapositive. It's sort of a natural instinct for a lot of people to respond to statements about notness that way, but not everyone does that naturally. And in under stress, you won't always do it. And so just point out that, yeah. So the classic is all the way back in Maths 1M or A, when they go prove that the square root of 2 is irrational. And the definition of being irrational is that it's impossible to write it as a fraction using integers. So you're trying to prove that something's impossible. That means it's much easier to do it by contradiction and suppose it's possible. Yeah, that's an impossible. Just, damn it, I'm going to not say that. I'm going to say not possible because then that matches with the vibe that I'm going here. So just be clear about that, and that makes it a little easier to choose a contra argument. So whether you choose contradiction or contrapositive is sometimes a bit tricky, and sometimes they look almost identical, those two proofs. If you can do it by contrapositive, most people prefer that over contradiction. There are some mathematicians who will not accept anything is true if it's been proved by contradiction. Whole realm of mathematics that doesn't allow proof by contradiction as a type of thing. But most mathematicians are just not that anal about it. And it usually depends on probably when you contradict. Let me think about this. Okay, so here's the thing. If your statement's an if-then contrapositive usually works as opposed to contradiction. But if your statement is just a it is, then contradiction is the only way because you can't contrapositive and this is statement. So And if, sorry, not contrapositive, contradiction. And if then, that's what I would generally do. This is the first time I've thought this, so I don't know if it's good advice, but you definitely can't do contrapositive if there isn't an if-then statement, because that's what contrapositive is. Contrapositive is an action you perform on an if-then statement to turn it into a different if-then statement. Yeah. Actually, that's kind of cool. I've never thought about it that way. Yeah. I have to keep an eye on that one. So they're my thoughts on it so far. I hope they're helpful. When you look at proofs in the next few weeks, have a look at the ones that have been done and see if you can find those patterns. Yeah. I hope that's useful. Helpful. Yeah. Okay. Let's talk about these Cauchy sequences. I may look this up in a minute, but I'll also get all of you to help me figure this out. Okay. So sequences are a big thing in real analysis. And it's actually really clever. It's a way of turning something that's continuous into something that's discrete, and to think about approaching something one step at a time as opposed to smoothly. I kind of think it's cute, the concept of sequences. But anyway, let me just see if I've got this terminology right. They normally write it like this. Do they put it like an n equals 1 to infinity, or just... Okay.
Like an n in numbers.
Like that? Okay, cool. And the idea is that what this means is there's a list of A1, A2, A3, A4 forever. And it's not impossible to start at A0 if it feels right. Okay, cool. Incidentally, that's what the natural numbers are for, making lists. Well, yes, the natural numbers have two purposes. They are for saying how many, and they're also for saying which one. Yeah, like A3, the third one. So this is actually, these 1, 2, 3, 4 is really the first, second, third, and fourth. So it's kind of cool. This is on my mind because I'm writing a maths course at the moment, which starts with what purposes of numbers are. So the natural numbers, the reason we still have them in maths is because we can make statements like this to mean, you know, it's for listing things. So yeah. So sequences look like that in your mind. And you can imagine them in multiple different ways to help you think about what they're doing. So you can imagine them as a graph like this. This is n and this is an, and you can say, well, here's 1 and there's A1, and then 2 and there's A2, and then 3 and there's A3. Like that. That's one way of imagining it. And if you really want to, you can connect them up, but you don't really need to. And it goes on forever like that. That's one way of imagining what the sequence is doing. And this one's really useful for thinking about the concept of the limit of a sequence, because you can draw a horizontal line and go, oh, they're always close to this line. Yeah. The other way to think about, well, an other way of thinking about what a sequence is I might change colors for this, is to think about it as here's A1 and then we move to A2 and then maybe we move to A3 and then to A4 and then to A5, and that you just locate the number on a number line and you're moving back and forth along the number line following the sequence one step at a time. And in this version, you can imagine getting closer and closer and closer to a particular spot. And this is really tracking on the y-axis what these points are doing here. They're both useful ways to think about what a sequence is doing. Doing okay there? All right. Have your lecturers or tutors drawn either of these kinds of diagrams?
I mean, the bottom one's like similar.
Sort of.
Okay.
Yeah. Yeah, but both of them are useful ways of thinking about it. Because some people define a sequence as a function from the natural numbers to the real numbers, which is what this picture is. Okay. So the limit, before I talk about Cauchy, you just need to talk about convergence. Is that the word we use, convergence? So a sequence converges when there is a number that all of the, this is really floppy, but there is a number that the terms in the sequence get close to. And one of the big things about real analysis is to figure out exactly precisely what we mean by get close to. Yeah. Yeah. So, I just want to point out, it is possible to think about sequences not just of numbers. We don't do it in real analysis because it's specifically about just the real numbers, but you can think about sequences of anything. So for example, sequences of points in 3D space, and you can imagine them this way of getting, a list of points and jumping from one to the other and they get closer and closer to something. Or you can do sequences of complex numbers, for example, which would be in complex analysis, and those sorts of things. Or sequences of anything. Sequences of words among all of the possible words that could be. So as long as you have a way of thinking about what distance is, then you can think about convergence of sequence, which is what integration analysis has in it, if you ever do that course. It's like, well, we're now going to think about what distance means differently. Did Finna mention metrics at the end? Yeah. So, cool. Just wanted to flag it because it's kind of nice to know where it's going. And the reason I mention that is that the importance and usefulness of Cauchy sequences actually comes up in places where Cauchiness and convergence are different things. So for the real numbers, being Cauchy and converging are the same thing. But in other places or with other ways to measure distance, they might not be the same thing. Yeah, so just wanted to point that out. That's why it's an important concept. Okay, so here's the idea. So we've got convergence. The concept of convergent as an adjective is that, now let me see if I can remember the definition. There is a real number. Oh no, I think I can do this. There is, and like L in R such that for any epsilon greater than 0, there is an capital N in N such that again. Am I doing okay? For every N greater than or equal to N, the distance between AN and L is less than epsilon. Something like that. You can probably put some, what's that?
Pretty close to that.
Um,
For any epsilon, every epsilon.
no, it doesn't. Any and every in that context are the same. So yeah, that's a really important thing to know about mathematicians. When they say any, they mean every. Whereas in English, any means pick one. And every means pick them all. Whereas in maths, any means it will work no matter which one, right?
Yeah, sort of a flaming.
Yeah, so they're, yeah. Yeah, and so it is officially every, and you can use that, yeah, English grammar works either way, so it's okay. In other languages, they only have one word for that concept, and so it's a little easier. So to be convergent, there has to be this number that you're getting close to, and you have to specify what it is in order to tell if it converges. That's one of the features of this definition, which I'm just going to say here. So to use this definition to prove that something converges, you have to know what the limit is. It's kind of interesting, actually. Because you either have to guess what it is, or just know, or be surer than guessing. Yeah. So there are a few that you just know, like 1 over anything that goes to infinity goes to 0. That sequence there. And then this thing's called the limit, right? That's still the same notation as in Maths 1b, like lim n goes to infinity of a. No, it does not matter. Tradition dictates you should use the letters that are most used just so that everyone doesn't get confused. But in maths, you're allowed to use letters to be whatever you want. There's nothing stopping you for using an x as the name of the function and f as the name of the variable if you want. But it's just confusing. So yeah. Okay, so what this means is, I'm going to do it in both pictures. There is a number L, and no matter which epsilon you pick, no matter what the sequence is doing, 1, 2, 3, there comes a point, 5, 6, 7, 8, there comes a point where they're all in here. Something like that. And then that's the capital N. That's the idea. There comes a point where the rest of the sequence is all trapped inside this zone. Yeah. And the other way of looking at it from a graph point of view is that here's L and here's epsilon up and down from there. And your sequence is doing whatever it does. And there comes a point that forever after this point, it's all inside this zone. Yeah. Yeah, the neighborhood. And they're both sort of interesting and useful ways to think about it. Yeah. So this one, it's a spatial thing. Everything after that is this. This is a time thing. They're very closely related to each other. And the point is that that happens no matter how small epsilon is. You're saying, all right, I'm going to choose epsilon equals 1. There'll be a point here where everything's within 1 of the limit from that point. And epsilon is equal to a half. There's a point where they're all within that a little bit later. And epsilon equals a quarter. There's a point where they're all within that a little bit later. And so you kind of can imagine it as like here's, you know, +1 and ±1, and there comes a point where you're always inside that, and that's your n that goes with number 1. And then there's like a lower zone further down where they're within a half, and they're all within a half at this point. And then there's a lower zone further down when they're all within a third, and they get closer and closer and closer. That sort of idea. There's a Roadrunner cartoon where the Roadrunner runs down into a pipe, and the pipe gets smaller and smaller, and the coyote, I don't know if you know this, but it's okay. Yeah. And the joke is that when they run back the other way, the Roadrunner gets bigger again, but the coyote doesn't. But anyway, that's the so yeah, you're sort of getting closer. The zone that it's within gets closer and closer and closer. That's the concept there. I've never drawn this picture. I like it. Sure. Yeah, and so this is the position where you get within a half, and this is the position where you get within like a third, and so on. Yeah. Okay, or a quarter, or whatever you want to do. All right. Okay, that's being convergent. But what if you don't know what it's converging to? Can you tell if it's convergent anyway? Now, you've been given like about 15 convergence tests, comparison test and the ratio test and the limit comparison. I don't know, there's like, I don't know how many there are, but lots. Root test and I did say the ratio test. That's the one that's in Maths 1B, so I can remember it. But they're all essentially comparison tests. You compare them to a sequence that you do know does converge and compare it in some way. You either divide it by the other sequence or you do the root. Yeah. So that's all good. But all of them are really essentially comparing it to a sequence that you do know converges. So the ratio test, essentially you're comparing it to a geometric. Ratio test is for series, not for sequences. Yeah. And most of them are for sequences, for series, not for sequences. And a series is the running total. To tell if a series converges, you make the sequence of running totals, or the official name is partial sums, and see if that converges. Cool, okay, cool. Anyway, but what if you don't know what it converges to? Can you tell if it converges without knowing what it converges to? And that's what Cauchiness is. So being Cauchy is a way of telling if it converges even if you don't know what the limit is. And the concept is, it's like, oh, well, I mean, if they all get close to L, they must get close to each other, the individual terms. Right? So this is the thinking. If the terms get close to L, then they must get close to each other. And the getting close to each other, that's Cauchy. Yeah. Yeah. And so Cauchy is, yeah. And so Cauchy is, now let's see if I can remember the limit. You do not mention an L that it's getting close to. So you start straight up with the epsilon when you're doing Cauchy. Yep. So you say for any, if you like, I am not going to be consistent. For every epsilon greater than 0, there is an n in n such that for all m and n greater than or equal to n, the distance between AN and AM is less than epsilon. So when you compare the two of them next to each other, the difference here is that this one starts at the epsilon. You don't mention the L first. And that's the vibe. We try and tell if it converges without knowing what it converges to. So it turns out, I mean, Cauchiness was invented for the real numbers, but it turns out that with other places and other distances, you can be Cauchy without converging, which is puzzling. But there you go. But in the real numbers, they are the same, which is nice. So, yeah. So just pointing out that this means that the terms get close to each other. So we know, we've already reasoned that, and there is a proof for this. If they are convergent, then they will be Cauchy, because it makes perfect sense that if everything's close to L, they must be close to each other. But the point is that there's another theorem that says it works the other way. There's possibly one theorem that's got an if and only if in it. What does theorem 3.43 say? Okay, cool. In my head, they're very different ideas. Like this one is obvious from a like, well, makes sense. I haven't got the proof to go with it, but it makes sense to me. The other one I'm going, I'm not sure. I worry that there's some weird ass sequences that doesn't work for. I worry about that. And so the Cauchy implying converging is the one that's the big bit. The other bit's less surprising. Yeah. Do you want to do that proof, or are you happy to skip it?
I think
It should be in the book.
Yeah.
How do you two feel in the Zoom? Do you want me to do that proof? Okay. So what do you want? Want me to do it?
Yeah, we use the sketch.
Well, let's not look at his sketch. You're going to see me try and do it from scratch, eh? Theorem, I don't know what it is. I don't really care. What did you say it was? 13 point? Oh. Criterion? Ah, so since it has a name, you have to remember that theorem. If your theorem only has a number and doesn't have a name, then it's sort of good to remember it, but you won't be asked for it by number. But anything with a name, you can be asked what the theorem says. Yeah. Name means remember it by name. So, okay. So I'm going to do the first half first because it's the one that makes the most sense to me. Suppose sequence AN converges. Okay, so here's my thing. I'm going to try and prove, actually just a second. Let's actually write the statement of the theorem, just so I can show how I made the decision. A sequence converges if and only if it's Cauchy. That's the statement, pretty much. Okay. So part one, which is the one that makes sense to me just heuristically. Part one, suppose the sequence AN converges. And then somewhere at the end, I would have to say, therefore, the sequence is Cauchy. And this is my attempt to do a direct proof, because a direct proof is always the one that I would try. And I'm also made to feel like a direct proof would be good because both of these are, it has the property, neither of them say it doesn't do something. And so I'm not, my instinct isn't making me think to do contrapositive or contradiction. Yeah. But technically this is two if-then statements. And so you might have to prove the two parts in different ways. But they're both sequence does thing. And so I would do direct proof for both is my instinct. Okay, suppose the sequence converges, and it seems to me that it would be useful to know what it converges to L. And so I might as well start that. And somewhere at the end, I don't know if I have enough space for this, but somewhere at the end, I'd be saying, and I'll just write it on a separate piece of paper, therefore, AN is Cauchy. People who talk to me in the Maths Learning Center are familiar with me doing this, writing the beginning of the statement at the beginning and writing the end at the end and making them match up in the middle. Because that's what, and that's not, it's not about working to connect them. It's about knowing that a proof is a sequence of statements like a poem, and it has certain statements in certain places. Like if you write a sonnet, there have to be a certain rhyming scheme, and it will have to have certain words in certain places in order for it to work. If we write a haiku, you have to have certain words in certain places to make the syllables work out. And in a proof, you have to have certain statements in certain places. A direct proof that goes from here to here must begin with this statement and end with this statement. And it's just a good thing to know about how the proof works. So now I am going to think about what it means to converge, and I may not write this down, but to converge would mean that no matter which epsilon I pick, there is an n, so that if I'm further beyond that n, I am within epsilon of L. That's the thing that I'm thinking. And this would be that no matter which epsilon I pick, there is an n such that if I'm beyond that for any two numbers, then they're that close to each other. So in order to prove that something is Cauchy, when I look at the definition of Cauchy, I'm going to have to make that statement true. And this statement says for every epsilon, blah, blah, blah. And so this tells me the structure of the proof. My proof is going to have to say, let epsilon be greater than 0 because it's supposed to work no matter which one. And then I'm going to have to tell the reader what n is and then convince them that this works. So my proof is now looking like this. Let epsilon be greater than 0. Somewhere along the way here, there is this is n. And then at the end, you're going to say, I reckon I might have enough space to fit it on this page, actually. I'm going to commit. Okay. All right. The last thing I say before this is I'm going to say that this is less than epsilon. Right? It's the last thing I'm going to say. And then I'll go, ta-da, it's Cauchy. So I might just move that down one step just to give myself the maximum amount of space. All right. And I have to get this n from somewhere. And it seems to me that I can get it from here because this says that given an epsilon, there is an n that does something. So the being convergent forces an n to exist that does a thing. It's not, doesn't do this thing, but it does something. And so that's what I'm thinking, that the definition of convergent creates an n, and I need an n, and so I'll get it from there. I may have to adjust this statement a little later. Okay. So I may have to rub some bits out and fix this in a little while, which is like your where the hell did the delta come from? But I won't know that until I've written the rest of the proof. Okay, so I need this to be true. So I'm going to, let m and n be greater than or equal to. I'm hoping that I don't have to choose two n's, but bear with, let's hope. Let m and n be greater than or equal to n, and then the distance between am and an. And I'll do some equalses and some less thans, and I'll get to an epsilon at the end. That's my goal. That's what I'm expecting to happen. So it seems to me that I'm not going to be able to use, I'm going to have, this is where the less than epsilon is going to come from. That bit just there. And so I'm going to have to create an L in this statement in order to use that one. And so just let me think about a picture for a second. So there's L, there's epsilon. I know that all of them are within here, and I'd like to show that no matter which two of them I pick, then the distance between them is less than a particular epsilon. It seems to me that if they're all within this epsilon, then the best I can do is they could be right on the edge and they'd be 2 epsilon apart. Because they could be anywhere in here, right? So they could be right on the edges here and here. And I couldn't guarantee them to be less than epsilon. But if I made this distance epsilon 2, then they're less than epsilon apart. Because I need this distance to be epsilon. That's what I'm thinking about in the picture. So I just wanted to pause and draw the picture to just give me some intuition from the picture about what I'm doing, which means I reckon I'm going to put an epsilon on 2 here. So you don't have to say, let epsilon be epsilon on 2. You can just change this to be whatever number you want. So let epsilon be greater than 0, then there is an n, so that for all n greater than n, this is less than epsilon on 2. It works no matter what number you put in that spot, as long as it's positive. All right. Okay. And so this argument's saying that if you're within epsilon of L, then the distance between them can't be any less than, okay. Sounds like a triangle inequality thing to me. And that's, the MO in real analysis. So I reckon I'm going to do this. Stick a plus L and a minus L in there, which means I haven't changed anything, so that I can do this. Like that. And now I know this is less than epsilon on 2 because n is more than capital N. And I know that this is less than epsilon on 2 because m is more than capital N as well. And so that is less than epsilon on 2 plus epsilon on 2, which is epsilon. Cool, I did just manage to fit it in this space. How do people feel about the process I went through? Now, obviously, that's slower than what would have happened in an exam because I had to explain it to you along the way. But yeah, I'm just going to draw this picture in the corner just here so it's not on a separate page. Like that. That's what I'm thinking. I just want to put it in the picture here because no one needs to scroll to the next page to do that. Okay. Okay. So the other part is possibly the harder part, yeah? Suppose sequence AN is Cauchy, and then somewhere along the road, further down, therefore AN converges. And it seems to me that the hard bit of this will be figuring out what L is. Oh, do you know what? I reckon I should do this contrapositively. Because at the moment, so I'm actually just going to, this is my thought process here. Therefore, AN converges. I'm going to have to say what L is in here somewhere. And I can't think of a way of creating L from the information that is in the Cauchy statement. That's why this is such a surprising theorem, right? So it seems to me that instead of creating L, I'm just going to show that there isn't not one. Yeah. So I'm going to do it by contrapositive. So suppose AN does not converge. And then I'll get to the end and say, therefore, AN is not Cauchy. Yeah. And this is extremely only if, right? So, oh no, this is an if actually, but anyway, it's like we're saying, well, if it converges, then it's Cauchy, and if it doesn't converge, then it's not Cauchy, and so therefore Cauchiness and convergence are the same thing. That's the vibe of this if and only if statement. Okay, so there you go. That's how I made the decision to do it this way. I hope that's helpful in some way. So maybe we add to our list before, if you have to create something that doesn't exist without a theorem to tell you that it's there, maybe it's easier to do it by contradiction or contrapositive. Yeah. So this is going to be hard because not converging is difficult. Not converging means that no matter which L I pick, it's always possible to pick a later term that's far away from it. Yeah. And to not be Cauchy would mean that no matter which epsilon I pick, there's always an N that means that there are two terms further out than that are further apart than epsilon. Like just to read this statement backwards. So for every epsilon, oh, it doesn't matter. No, it doesn't matter which epsilon. There only has to be one epsilon that breaks it. Yeah, so Cauchy, this has to be true for all the epsilons. So if we break it for just one epsilon, it'll be okay. So if there is an epsilon where there's no N, such that if you're beyond it, you're within epsilon. And so that means that there is an epsilon that no matter which n I pick, you can always get beyond epsilon away from that. Yeah? Okay. Tricky. I'm just going to think about this picture for a second. Okay, but we can make a similar, oh, wow. That's okay. So I need to show that, I need to tell them what the epsilon is. Yeah? So I have to create something that currently doesn't exist, which means I have to get it from the fact that it doesn't converge. And the fact that it doesn't converge means that no matter which L I pick, there is an epsilon for which this doesn't work. Yeah? So to be convergent, there is a specific L that does this. And so for not convergent, there is no L that does this, which means that no matter which L I pick, it doesn't do this. Okay. Yep. No L does this. So all the L's don't do this. That's the same thing. Okay. So I choose 0. I don't know. I'll reserve the L for later. There is an epsilon greater than 0, so that for every n greater than or equal to n, there is an n that's greater than or equal to n such that the distance between this and L is greater than epsilon. That's the opposite, right? So what we'd actually like to show is that no matter if there is an m further out, then the distance between an and am is more than epsilon. Just going to draw my line vertically instead of horizontally. There's L. There's epsilon. Ah, there are infinitely many n's that do this. Okay. Yeah, no matter which capital N you got, there's always an n further out that does this, which means that there's just infinitely many n's that do it. Okay. And so they could be above or below. So if one of them's above and one of them's below, then we're good, right? Because they're 2 epsilon apart and therefore epsilon apart. So that's okay. Yeah. But you're not guaranteed to have another one below at any point. Wait, I'm nearly there. What if there were 2 L's and it was like close to like it? Yeah, I think I have it. What if, because if there are 2 L's, because the problem is that there's infinitely many that are this distance away from L, but they could all be on the same side, and that's not going to help me do the distance between 2 of them. But if I knew there were infinitely many close to like in a particular spot and infinitely many in a particular spot over here, then that'd be okay. So that's my guess, that if there were 2 L's, then there'd be an epsilon. I'm going to stop now for a second and consider advice from outside my own head.
I sort of remember
Hmm.
what's the subsequences. So we have to use whole line.
Okay.
I think the other fact I remember about Cauchy
Oh, they're bounded.
they have, well, yeah, they're bounded and they have a convergent subsequence as a result.
Oh, and that's how we create the L. Ah. Okay, well, this was a good try. Okay, wow, this is hard. So just a second. My problem with the previous one is I couldn't say what L was, but maybe I could think about creating L from some other theorem about sequences. Ah, oh, fabulous. So the thought now is, create L from some other fact about Cauchy sequences, right? That's maybe how I'm going to do it. Oh, and so there's a theorem that says that a bounded sequence has a convergent subsequence. That's called the Bolzano-Weierstrass thing. Okay. Okay, so the other fact is two S's on the end of Weierstrass, maybe. Are you allowed to just call it BW? Okay. And that's a theorem. Ah, okay. Right. Oh. So you make this convergent subsequence which converges to some L. And since every term in the Cauchy sequence gets close to the terms that are in that sequence, because they're all close to each other, they'll all get close to L as well. Sneaky. Sneaky, sneaky, sneaky. All right. So suppose AN is Cauchy. We're going to do it direct now. And we want to show that it converges. Yep, that's okay. I can do that. So we have to tell the reader what L is somewhere in here. And then we can show that it converges by picking an epsilon and blah, blah, blah. So to show it's bounded, I probably have to pick an epsilon, whichever epsilon I like, and show that it's bounded for the bit after that, is what I'm going to say. So if you pick like the first term and like the number 1, no, just a second. Yeah, just pick. Yeah. Well, no, bounded is that everything is within a certain zone of one number. Yeah, bounded is like the weakest kind of limit, if you think about it. So, you know, this thing that we said before that said that there is a zone that all the terms of the sequence are within. That's bounded, but we don't make it smaller and smaller. We just go, that's enough for me. So bounded is essentially, oh, that's so cool. I've never thought of it that way. Converging means that there is the later part of the sequence is bounded by tighter and tighter bounds. That's so cool. Huh. There you go. I like it. Huh. What's that? So you can see the number 1. There is an n in n such that for all m and n greater than or equal to capital N, the distance between AM and AN is less than 1. Yep. Because you just need one number to make it work. So in particular, the distance between AN and A capital N is less than 1. And therefore, AN is between AN plus 1 and AN minus 1, and therefore is bounded from that point forward. Yeah. So AN n equals n to infinity is bounded. Yep. Is that okay? Right. Well, let me do it around this way with an M and an N, because then it's easier to see that I've replaced this one with the capital N. So it works for all the M and N greater than or equal to N. In particular, it works when this is a capital N, and ta-da, and we're good. Okay, that's fun. Okay, so that is the proof that the Cauchy sequence is bounded as a separate proof, which I'm sure is probably a lemma in the course, but I didn't know what that lemma was, so there's my lemma. Cool. Well, we've done that lemma now. And if you want to show the whole sequence is bounded, that's okay. There's only finitely many other points in here, and so they're guaranteed to be bounded by whatever the maximum and minimum of them is. So, yeah. Okay. And therefore, by Bolzano-Weierstrass, there is a subsequence which converges. Yep, that's what that theorem says again. Yeah, okay. That L be its limit, because now it has one. We have created the L we need. Right. I just need a picture at this time. I'm just going to do it this way. So we've got our Cauchy sequence. We've got our L, and there is a subsequence that goes there. Yep. That's our subsequence that we're interested in. And then there's all these other terms in the sequence, possibly. Like that. And the concept is that because these ones get close to L and these ones get close to these ones, they'll get close to L as well. Yeah. Well, now we are up to, we've got the L. We can now say let epsilon be greater than 0 and run along the proof for being convergent, which says you have to say epsilon is greater than 0 and you have to specify what capital N is. It's different to this capital N. So I'm going to call this one by a different letter, if you do not mind. I shall call this N1. The reason I've done that is I would really much prefer the other one that I'm about to find to be called ordinary N. because it matches better with how the statement of the theorem goes. There's nothing stopping me calling the later one n dashed or something, but this will make me feel better. This is just my preliminary n to show that it's bounded. So if you did have this as a separate lemma, then you could just say, not mention this n, and it'd be easier to write. So that's why people have lemmas, so they don't have to mix up their notation all the time. And plus they can reuse them lots of times. It's repeatable reasoning. Okay, so let epsilon be greater than 0. We have to create an n, and we do have an n. We know that there is an n in n such that for all m and n greater than or equal to n, the distance between am and an is less than epsilon. This is true because it's Cauchy. So we're over here, and these are all less than epsilon apart from each other. Okay. And so what we'd like to show is that this means that the distance between an and L is also less than epsilon, but I may have to adjust this epsilon in order to do it. Feels triangle-y, right? Oh, no, wait. We're using the convergence to do this, not the Cauchiness, yes? Right, just a second. No, we still need that. We could get this n from the convergence of, this sequence, or from the Cauchiness. Oh, there's two of them. We need the red ones to be close enough to L, which gives an n that comes from the convergence of that subsequence. And we need the other ones to be close enough to each other, and that comes from the Cauchiness. That's two different n's. We just need to be further than both of them in order for it to work. So you're right, we do need to call that subsequence a name so that we can refer to it. I will use K. A-N-K. Yep, I will just call it BK. So it is tradition to go A-N sub K, but there's, if I've got subscripts in subscripts, it's just going to get ridiculous. So I'm just going to give it a whole new letter, knowing that BK is A-N-K for some NK, basically, for some, yeah. No, BK is A-N-K for some NK, right? Because it's a subsequence. Okay, cool. So there is an n in n such that for all m and n in, so I'm going to call this one the Cauchy C. Oh no, they both start with C. Oh, crap ass. The other one can be NL. That's okay. The distance between AM and AN is less than epsilon. And that's since AN is Cauchy. And there is an NL in N such that for all N in greater than, damn it. Okay. So what we are trying to show, no, this is BN, right? Oh, I could have called it capital K. That's okay, it's there now. All right. Well, BK is one of these things. Yeah. There'll be a triangle inequality somewhere, right? And our goal is to show that AN, this is the goal here, or something or other, right? And so that statement needs to be pulled apart. That's the thing that's pulled apart with the triangle inequality, not either of these things. Yep, I've got it. Okay, so we've got that AN minus L. We've got to put some words in here in between. Something like that. Yeah. What's that? Oh, yeah, these need to be epsilon on 2s. So that when we split this apart, we've got 2 epsilon on 2s. And then we just have to be sure that the K is far enough out for the NK that it really is to be further than this one. And that the K is further than this. Because this BK is the M that's being referred to here. So we need to choose N to be more than this. Yep. And K to be chosen such that the NK that it really is more than that. And it's also more than this. So choose. Yep. Choose K so that K is greater than or equal to NL and NK is greater than NC. I'm glad I mentioned the NK earlier. You know, BK is equal to ANK. That probably wasn't necessary, but that's okay. I've committed to it now. So we choose K so that K is greater than or equal to this number and NK is greater than or equal to that number. And that means we can use this because it's more than that. And we can use this as long as the N is also more than NC. And so we can say for N greater than or equal to NC, we've got this statement now. And we're there. I'm going to have to read that forwards to make sure it makes sense. Okay, here we go. Suppose AN is Cauchy. Consider the number 1. There is an N1 in N such that I was happy with this bit. That bit's fine. I'm all good with that. That's our lemma. By the Bolzano-Weierstrass theorem, there is a subsequence which converges that BK, K is 1 to infinity, be this subsequence and L its limit. Note BK is equal to ANK for some NK and N. Let epsilon be greater than 0. There is an NC in N such that for all M and N more than NC, the distance between AM and AN is less than or equal to epsilon on 2 since AN is Cauchy. There is an NL in N such that for all K in NL, BK, I should have called it a K. That makes much more sense. I'm going to call it K. This is now N. All right. There is an n in n such that for all little m and little n in greater than or equal to big N, the distance between am and an is less than epsilon on 2 since it's Cauchy. There is a k in n such that for all little k greater than or equal to big K, the distance between bk and L is less than epsilon on 2 since the limit as n goes to infinity of bk as k goes to infinity is L. That's that statement there. Now we're going to choose k to be any number that is greater than this k and such that the nk that it goes with is greater than that n. And that means we'll be able to use both of these as long as we use nk in this spot here. And then no matter which n is bigger than that, the distance between an and L is the distance between an and bk. And I should say ank probably here just to be absolutely clear. Yeah. And so this is less than epsilon because both n and nk are more than n. And we are using this statement. And this one's less than epsilon on 2 because k is more than big K as well. And therefore we're done. And so an converges. Oh, wow. So unless you had seen that proof already somewhere, I wouldn't expect your lecturer to put it in an exam. But now you've seen it, you know. And so lecturer in the notes did a sketch of it. Was it one of the exercises?
Yeah, it wasn't an active sketch.
Okay.
Yeah, converges implies Cauchy is the integral.
Yep.
As direct point. Then the other way, first show Cauchy sequence bounded, second both Designer and Weierstrass. Third, show a Cauchy sequence with the convergent subsequence in self-convergent.
Okay. And so that was the tricky bit, the last statement there. I'm kind of happy with this. You saw, I hope it was instructive to see that happen. Yeah. There was probably, no, I don't know if there's an easier way than that. I mean, I did that. But I get the concept of what it was. So if you're ever in an exam and you can't figure out the details, you don't have time, you can say, this is the concept, and you can literally describe what you're trying to get at. You can say, I've found a subsequence. I know that that sequence converges so that its terms approach L and the rest of the terms of the Cauchy sequence approach each other and therefore approach these, which approach L, and so they'll all approach L. If you couldn't even figure out how to do the whole thing formally, you can at least describe the vibe of your proof, and it's a good start, and you'll get something for the exam because you've shown that you understand how to think about these things. Yeah. Wow. Cool. The thing that I find the most weird and cool about this one is that this statement was only used to pick a specific K, not all the Ks. Whereas this statement, we picked all the N's and one of the M's, which was NK. I think that's fascinating. It just shows the possibilities in these proofs, is that sometimes you can just pick a specific one. Right. And there was another bit there that I thought was interesting that I said that I didn't realize until the time. The statement I wanted to make was that an minus L was less than epsilon. And I said, this is the thing I want to use the triangle inequality on. I don't want to start with these and use the triangle inequality because I want to use these two statements after I've done the triangle inequality. And so this is where I had to create the things that split apart. So that's probably a thing that happens regularly in this part of a proof, where if you use the triangle inequality, the things that happen after have to be the things that are less than something. Yeah. So, because my first instinct was to pull this apart with the triangle inequality, but I paused for a moment and didn't do it and went, actually, what's the statement I need to make? I need to make the statement that this is less than epsilon. So I'll pull that apart, because then that's part of my equals less than thing. Yeah. Cool. Wow. Yeah, once you're here, then it's fine. And not until I wrote this down did I know that I had to make these epsilon on 2s. Should be great. When I did one of my third year integration analysis, there was a proof that I had done before, like it was in one of the tutes, and I couldn't remember it, and I kept coming back to it over and over and over. And then I scrolled the whole thing down in the last 5 minutes. I suddenly remembered what the missing bit that made it work. I got 100% on that exam. So that's my story of do not leave an exam early, even if you can't. If there's one question left you can't figure out, then maybe inspiration will come. Last 5 minutes. Okay, so I know there's about 20 minutes left. I can keep going after that if we feel like it. But I do want to go back to our list of things to do. And I want to take something here about the fundamental theorem of calculus. This is one that's a bit vaguer to me. I'm not really 100% sure on the shape of this course after the fundamental theorem of calculus is introduced. But I do know that we now that there's 2 parts to it. And I'm really hoping that this is what they are. And so maybe I should just look them up. But let me try and remember first. It's always good for you to try and remember, or maybe you can try and remember first. My memory of it goes that part 2 is this bit. Is that right?
Yeah, that's our part 1. Okay.
Spiritually, in my own feelings, it should be part 2, but yeah, that's okay. And this one is, I'm just going to make a guess, that the function you create by doing the running total integral of the running total area of another function is differentiable, and its derivative is the function you first thought of. So something like this, let f of x be the integral from a to x of f of t dt, then f is differentiable, and f dashed x is little f of x. Is that what it is?
Yeah. There's the immediate result that f is continuous, but the little f is continuous on the interval.
So just a second.
It doesn't guarantee.
So part 2. So suppose f is continuous. So if f is anything, if f is defined, then this function is continuous.
So it's defined as integrable.
Integrable.
Big F is always continuous.
No, if little f is it's integrable, then big F is continuous. And if little f is continuous, then big F is differentiable. Okay. So just a second. So suppose little f is integrable on some domain that involves A, right? Then f is continuous. And if f is also continuous, then big F is differentiable, and f dashed of x is little f of x. Yep. Right. So I can see why it might be part 2, because it's hard to say. But it feels to me that it proves the existence of functions that do this. But anyway.
Yeah, I mean, it serves that role, I guess. The first part sort of like uses very specific type of function. It does this, and then the second part is actually for that second function. Guarantees.
So
Gives meaning to the first part.
yes. So I'm just going to repeat that. The part 2 gives meaning to the first part by saying how to create a function that is an antiderivative of something else, which is to do the running total integral. Because integrals have a separate definition, right? So you define integrals as like the number that is both the infimum of all the upper sums and the supremum of all the lower sums, right? And if there is one number that's both of those, then it's the integral. Yeah. And integrable means that happens. Yep. Okay. Just making sure. And just checking, in this course, upper sums don't have to have equally spaced intervals. You can do whatever intervals you like. But if it does, there's like a corollary, I think, that says that if the equally spaced intervals works, then it works, but that's not the definition. Yeah. What's the name for this thing? Like this infimum of all the upper sums? It's like an upper integral and a lower, I don't know. Anyway, that's all right. So anyway, my understanding of the fundamental theorem of calculus, of this part of the fundamental theorem of calculus, is it tells you how to do integrals in the way that you are familiar with doing integrals. By, you know, power up by 1 divided by new power, that sort of thing. Yeah, but I would love to see a proof where it was used later on to do something else. Integrals are at the end, or are they?
Yeah, they're chapter the 7.
Whoever asked that about the fundamental theorem of calculus, did you have anything in mind? Where's the contents? Right. Here's a bit on the fundamental theorem of calculus. F sends A to B to R is integrable and F A B is differentiable. Theorem 7.12 says that every continuous function is the derivative of something. Yes, okay, cool. The benefit of being able to compute integrals using antiderivatives cannot be overestimated. Ah, well, there's a corollary, which is the mean value theorem for integrals, which may be useful. So I think one of the things, okay, cool. Glad to hear it, that clears things up. I will just say that there's a corollary, yep, which is the mean value theorem for integrals, which says that if G, which sends A, B to R, is continuous, then there is a C in AB so that the integral from A to B of G is B minus A times G of C. I'm going to draw a picture of that because Finner doesn't have a picture of it in his book. He may have done it in the lecture when he talked about it. What the hell? Anyway. So here's A and here's B, and here's G doing whatever G does. What we're saying is that there is a height, there is a function value somewhere along the line here that you can pick so that if you draw the horizontal line at that spot, then the area of this rectangle is the same as the area of the function. That's the idea, that you can flatten out a function so that its area is a rectangle. And you can do it by picking at least one of the function values. This function's got two of them that do it. And so you can sort of smush this bit into those gaps and it all works out to be a rectangle. That's what the mean value theorem for integrals is about. And the definition of the average value for a function in many courses is the integral divided by the width. Yeah. So I've known this as the average value theorem. Yeah, as opposed to the mean value theorem. So the average value for a function is what you get when you spread the area evenly across the space. And so you could say that, you know, the average value of G on AB is the integral from A to B of G divided by B minus A. Because you spread the area evenly across the space and you get this average value. That is the function that you would have had if the flat function that would have produced the same area. And the point of the mean value theorem for integrals is saying that there is, in fact, a function, an input that will produce the average value. Yeah, it's kind of cool. And so that's a corollary of the fundamental theorem of calculus, and also a corollary of the mean value theorem for derivatives. Yeah. Do I feel like doing that proof? No, we won't. Okay. Yeah. To me, this is what integrals are. The entire point of integrals is actually, in my head, to find average values. Yeah. I mean, I know that the point is really to accumulate the function value across a space. Like, the physics purpose of integrals is really important. It's like you've got a rate of change, and so you know how quickly things are changing over time, and so you accumulate all those little changes and you get the big change. And that's what the integral is, it's the accumulation of that change. But for me, from a real analysis point of view, this is where integrals were heading all along, trying to find average values. And the reason we did it, and I know this because we were drawing rectangles the whole time when we're doing upper and lower sums, upper and lower integrals, or whatever they're called. What were they called? No, lower sums, upper and lower sums. But there is an upper integral and a lower integral. Yeah, the lower integral is the supremum of all the lower sums. And the upper integral is the infimum of all the upper sums. And so what that means is, this is really cool, this is one of my favorite things, that if you find any partition and find the upper sum of that partition, the integral, if it exists, has to be less than that number. Yeah. And if you have any partition and you find the lower sum, the integral of the function, if it exists, has to be more than that number, because the integral is the supremum of all the lower sums, and so it's greater than or equal to no matter which lower sum you pick. And so if you have a function that's defined as an integral, such as, for example, ln of x, or log of x as this lecturer calls it, then you can say, by choosing your partitions just right, that it's greater than various different things. Yeah. So that's just a useful, interesting thing. You don't have to choose equal partitions. You can choose whichever one makes sense to you. Yeah. Anyway, there you go. I am in my bridging course, I didn't use equal partition upper and lower sums to define integrals because I wanted to use a real analysis idea. And so there are several exercises in it that say, here is a function, show that its integral is more than this number. And if you, by choosing an appropriate partition. Yeah, I just think it's cool. Okay, what was the other thing on our list? We've got 5 minutes. Well, we've got 2 minutes. I'm going to do it. The sequence definition of compact. Compact. 41. Is it defined with sequences to begin with?
Yeah.
And then there's a theorem that says that it means the same as closed and bounded. Mm-hmm. Probably. So let's see.
In every case, this works.
Compact if every sequence in K has a subsequence that converges to a limit in K. So that's the definition. And then there's a theorem which has a name. It's called the Hein-Borel theorem. Compact if and only if closed and bounded. So that's the definition. And this is a theorem. And so theoretically, if you were to prove this theorem, you would have to use that definition because the theorem doesn't exist yet. Yep. And so you have to understand how this definition works in order to prove at least one theorem. Okay, so it does make me wonder why the definition has been chosen this way. So way back in Maths 1A, we defined linearly independent for vectors in a particular way because it was particularly useful for doing proofs. But this doesn't feel useful for doing proofs. But it would be easy to show that something wasn't compact, right? Yeah. So I think we're going to make a comment here. Maybe.
Yeah, I think
it's easy to show a set is not compact. Okay. Wait, Wait. No, okay, cool. No, so I was saying, isn't the entire real line compact? But no, it is not, because not every sequence has a sequence that converges at all. Cool, that's okay. Just the bounded one, right? Cool. So it's, well, easier, right? Easier to show that something's not compact, because all you have to do is find a sequence that converges to a limit that's not in K. That's one way of doing it. Or show that there is a sequence that doesn't have any subsequences that converge. Or show that there is a sequence. Yeah, so there's lots of different ways to show that it's not, because you could break this at any point in its statement. You could break part of it, and so that would be okay. So, e.g., find a sequence with no convergent subsequences. I mean, that's a really extreme way to break it. Just not have any convergent subsequences at all. Because you technically only need one that doesn't, that it might have a convergent subsequence, but the convergent subsequence converges to something that's not in the set. So that's okay, you know, or convergent sequence whose limit is not in the set. Yep. So I know, for example, I can show that any unbounded set isn't compact because I can make a sequence that doesn't converge, like that has no convergent subsequences at all. So just as an example, the interval from 1 to infinity is not compact since sequence n has no convergent subsequences at all. And since it doesn't have any convergent subsequences at all, it can't have convergent subsequences that converge to a limit in the set. Yeah. And 0, 1 is not compact since zero, which is not in the set. This sequence has to be inside there, of course, for it to work. But since it contains that sequence. So it's much easier to show that things aren't compact than it is to show that they are. And since that seems to be the case, that it's easier to show that things aren't compact than to show that they are, then it might, you're right, be easier to go contradiction to show that something is compact. Like, suppose that it's not. Here's a sequence. Oh, no. Yeah. But I don't know. Have you got any exercises off the top of your head that go with that? Oh, yeah, 4.8. I mean, it feels direct. It is an if-then statement, not subsequence, a finite subset. Yep, sorry. I just want to draw a picture of it. here's my finite set. I have an infinite sequence made in only of these finitely many things, right? So I'd have to, my sequence can only jump around between these numbers, and it jumps around forever. So one of those numbers has to happen infinitely often. And that's a perfectly good subsequence that converges. So this is a direct proof, I reckon, just based on the picture. So that would be my argument. Let K be a finite set in R. And let AN be a sequence in K. Maybe we'll say with or K, little k elements. Yep. So at least one of the elements of K has to appear in this sequence infinitely many times. Because if they all appeared finitely many times, this sequence would be finite. So that's the infinite pigeonhole principle. If you have infinitely many pigeons to put in finitely many pigeonholes, then one of them has to have infinitely many pigeons in it. So not that anyone calls it that, but that's what I call it. So you can say AN has infinitely many terms chosen finitely many options. Therefore, so I don't even need to mention the K back there. I choose not to do that. After all, there is an element K in big K, which appears in the sequence infinitely many times. Suppose the positions as appears are N1, N2, N3, etc. And so then ANJ is a subsequence that is constant. Yeah, and therefore converges. Do K because it's always K. I think that's good. And this proof was almost entirely words, and that's okay. Yeah. But I didn't know in advance. It felt, our instinct was that we might have to do it by contradiction. But the picture told me actually I could just make the sequence I need.
And this is efficient every
Yep, because every sequence has to have infinitely many terms that are all the same number, and that's the subsequence I pick. Because I only have to pick one subsequence for every sequence, but you're right, you have to check that it works for every possible sequence, and it does because there's only finitely many options to choose from. That's a really satisfying little proof, actually, but it can only be done in word. Well, I mean, I'm sure you could do it with more symbols than I did, but it's not worth trying. What's that? Yeah. Yeah. That's cool. Huh. If I wanted to make a moral of that, it's never a bad plan to have an imagining of what the situation looks like. Yeah. And you'll notice that this was I could have drawn the other picture, but this one helped me more probably than the other one would have, because I knew I was bouncing around all within the same things. Yeah, so cool. Which means that a finite set is closed automatically from the Heinberg theorem, but you can prove that separately to that. Well, I think it's time to stop. Thank you. I